Okay. When it comes to zero input response or unit step or unit impulse response, there are other some interesting things we can talk about. Okay. For instance, let's go back to look at the unit impulse response. Always remember unit impulse response is the special case of zero state response, where the input is the unit impulse signal. So this is what we have. We have a delta function. You send it to a linear time invariant system. Assuming zero state, then the response will be your h of t. Assuming zero state. A few questions that will follow. Now, if my input is changed to t minus capital T, meaning the spike will not appear at t but capital T, and send this to the same linear time invariant system, what will be the corresponding output? But without any calculation, because the system is time invariant, we know the output should also be delayed by the same amount, and nothing else will change. Okay. This is about the time invariant. Now, remember in chapter 1 we talked about system being causal. Causal system means the output at a certain time instant should only depend on the input at the same time instant and or in the past, but nothing in the future. So meaning you cannot respond to future input when you haven't received them yet. Now in terms of impulse response, how do we quantify it? Again, remember the unit impulse response implies your input is applied at time 0. So if you're looking at a causal system, h of t should remain 0 for all the negative time, meaning before the spike appears, the system should remain quiet. Shouldn't respond at all. If this one is violated, then the system is non-causal. Okay, this is by looking at h of t and figure out what happens. Okay, so this is causality. Now, what else can be looked at when we are dealing with the impulse response and the zero state response? Now, we can think of some special input. Now, in the table, you're given all kinds of pairs of f1 and f2 to calculate the convolution integral, and almost all of them have this u of t in there. U of t is a switch. Remember, it's a switch that turns on at time 0. But sometimes we give those signals some name called causal signal. So a signal is causal if the signal remains 0 in the negative time. Okay, so this is what we have. Impulse response, or unit impulse response and zero state response are strongly related, as we all know. And since we're all clear how to do the calculation, this gives us a way or the complete solution to find the total response of the linear time invariant system. Because at the beginning we have already figured out how to calculate the zero input response, and now since we know how to calculate the zero state response, everything is set. The zero input response, we know, well, eventually the form or expression of the output of the zero input response should take a form like this. Have a bunch of exponential signals with the CIs calculated based on initial condition. The zero state response will be what? Will be your input convolution integral with your unit impulse response h of t. That's your h of t. Now, if you remember from our previous discussion, I can scroll up my lecture notes. We did some example, and this is we found out that almost always when we figure out h of t, the unit impulse response, it also looks like this e to the lambdas, e to the lambda t. If we look up to, let's say, our discussions and examples right here, for this particular example, we also mentioned, well, for this example, you have two characteristic roots, -1 and -2, and when you eventually obtain your impulse response, h of t, you still have this e to the negative t and this e to the negative 2t. Both of the terms appear in the zero state response. Now, that's your h of t. It also has this e to the lambda I t terms in there, but with some constants. But this f of t can contain some additional terms beyond this lambda t. For example, we looked earlier in our example, for instance here, when our h of t is calculated to have e to the negative 2t, and my input f has this new exponential term e to the negative 3t, the corresponding output will have this e to the negative 3t terms as well, in addition to the e to the negative t to the negative 2t. So you have some additional terms that comes from your f of t. So there comes another way to organize the terms. That is, we can sum up all this e to the lambda it's. Of course, there will be some coefficients, undetermined coefficients, and there are some additional terms, like the e to the negative 3t in our example. As we discussed before, if you scroll up the lecture notes, you will see these e to the lambda it's, because all the lambdas that are defined by the characteristic equation, and the characteristic equation comes from the differential equation, they define the internal property of the system, so they are called the modes. Since they define the internal property, this particular term is usually referred to as the natural response. Well, the additional terms usually comes from the external input signal is sometimes called the forced response. That is something coming from outside. No. From the system's perspective, total response equal to zero state plus zero input is a very useful way to do auto calculation. In some other scenarios, it may be interesting to calculate this here, the total response, especially to look at the forced response. So, to see how this will turn out to be, we'll look at some special cases of the forced response. And see how this will turn out. Now, when calculating forced response, there are usually some ways to guess the form of the forced response. And as I mentioned, we only look at one special case. The special case is when the external input takes an exponential form. And it's an everlasting exponential signal, as you can see. It's everlasting. There's no switch to turn it on at time 0. It originates from t equals infinity, beginning of the time, and ends also at t equals infinity, also meaning it's always there. There's no end, there's no beginning. Now, if this is the case, the forced response will also take a similar form. For the forced response, we use the term y sub phi of t to represent. That's the forced response itself. It turns out the forced response will be equal to a constant beta times the same exponential signal, e to the st, where s can be any complex number as long as it's a constant. So the immediate question will be, what is the value of beta? What is the value of beta? Now, this type of derivation we have done it earlier. That is when we have our differential equation at the beginning. Plus all the terms, a1 dy dt plus a0y equal to bn dnf dtn up to b0f. Now, since we now have my input and I have an output, I can plug in this equation. So the output will go to the left hand side, and the input will go to the right hand side of the equation. So plug it back in. Since you take the derivative of the exponential signal, you always end up with the same exponential signal. So eventually on the left hand side, you'll end up with the following. You'll end up with s to the power n plus an minus 1 s n minus 0 times beta e to the st. Okay. On the right hand side, you will obtain something very similar. Also a polynomial of s but of course, since the input signal is just e to the power st, we have e to the power st. we use this trick to derive the zero input response at the beginning. And at that point we have the polynomial of lambda instead of polynomial of s, but we'll just change this to another symbol, but the idea is the same. If you still remember, we call this polynomial a Q polynomial, but now the variable will be s, and this guy we call it P polynomial. Before we have polynomial of d or lambda, but here the variable will be s, so we can put s. Then you see there are two e to the st, they can cancel each other, and this equation will give me something interesting. That this beta is equal to the division between two polynomials. Underneath there should be all the a's, b's, a1 and a0. What does this mean? We'll give examples. Case number 1. If your input is a pure constant, and let's say this constant is real, for simplicity, then it can be written like this without an issue, meaning s equal to 0. Then the forced response, according to what we have earlier, should be equal to c times beta times e to the power 0t. Because now we multiply by c, according to linearity, the response will also be amplified by the same factor. Or will just be c times the beta will take this form, but since s equal to 0, I have to replace all s with 0. That will end up with just b0 divided by a0. Example. We use the same example, for instance. d2y plus 3 dy dt plus 2y equal to df dt plus 4f. If my input is f of t equal to 5, for instance, then my forced output equal to what? Equal to the amplitude of my constant y times b0 being 4, a0 being 2. So at the output I should have constant 10, meaning the system is actually amplifying this by a factor of 2, or double the amplitude. Now, in general, what we can do is, let's call this, since you have a bunch of s can be anything, we can just view this as a variable, so we call it h of s. H of s is a function of s, is calculated or defined as the division of two polynomials. The denominator polynomial comes from your output part of a differential equation, while the numerator polynomial comes from the input side, okay, with the b's and with the a's on top and underneath. So if we put it as function of s, then the forced response in this particular case can be written as c, the amplitude of the input, times h of s equal to 0, right? This is what we just did. We replace all the terms in this polynomial, all the s in this polynomial to be 0. So all the s terms will be 0, you're only left with the constant terms of b0 over a0. Now in your circuit theory, this constant value is called what? The constant value is sometimes called the DC signal, right? It's direct current. Doesn't change over time. And Hs equal to 0 is sometimes called the DC gain of a system, of a linear time invariant system. And it's very intuitive because this guy is the amplification factor that the system will apply to an input, to a DC input. That's why we call it DC gain. How much gain you will observe when you put in a constant DC signal. DC gain. This is the first case. Case number 2. Now we can play a little trick. This trick is called having my input signal f of t equal to e to the j omega t, meaning now s is equal to a pure imaginary number j omega. Now according to this discussion we have above, the forced input will be equal to, of course, according to linearity, you should have this a times beta times e j omega t as before, and this beta is simply my h function of s, with all s replaced by j omega. Okay. Along with this special case, let's consider another signal that look like this. So s equal to negative j. This will implies what? This implies another forced output. Will look similar, but will be s equal to negative j omega. Right? If this is the case. Now, having a j omega may not look that comparable, right? We are all interested in something more straightforward. So let's use our Euler's formula, which means we can break down this guy into two terms, two sinusoidal terms. One real, the other is complex. So if this is how I break it down, the corresponding output can also be broken down, and will be broken down in the following manner. will be the real part of h as equal to j omega. ej omega t plus the imaginary part of the same thing. A here, I have also a here. Now, according to, again, linearity, you can view this as two inputs. One is the real part, cosine, the other is the imaginary part, sine. And one is 1 multiplied by cosine, the other is j, another constant multiplied by sine. Now, according to linearity, the real part of the input will lead to the real part of the output. So that means if your input is a cosine signal, then your output should simply be equal to the cosine signal as well. And this cosine signal can be done in the following manner. So A, as we have, h of s equal to j omega, I can just write it as h of j omega. Right? And we have e j omega t as usual being the real part. Then the question is, how can we simplify the calculation of this guy? Now we're dealing with complex numbers because of the j's. So we'll look at the complex numbers. There are two of them. This is one of them. This is the other one. Now, what I can do is I can rewrite the first term in the polar form of complex number. In other words, I have to find the magnitude of this one, the absolute value, and the angle. If I'm not sure how this is obtained, you want to refer to the background material chapter. Now for the second one, it can remain by itself, such that the forced response in this case, if we only focus on the real part, will be A times the absolute value of j omega times e to the j omega t plus the angle of h j omega. Now applying the Euler form, because now the only complex number will be this guy. And applying the Euler's formula, will end up with the following equation. Because we're taking the real part, and the real part of this guy is simply a cosine. And that's it. And the conclusion we have is, if your input is the cosine, the forced output will be again the cosine signal, and this cosine signal will have the same frequency, omega, but the amplitude will be amplified by the amplitude of this h function, and the angle of my cosine signal, or the phase of the cosine signal, will also be modified by the angle of this h function again. And because of this h function is so powerful, we simply just give it a special name, h of s. We call it the transfer function, because it tells us how the output and input are related. Now, next we'll use an example to illustrate this more complicated cases where the cosine signals is involved. Hopefully that example will help you understand this part a little better.